going to skip to the AP exam from 2013, and this is going to be the free response portion. This is number 3, so this is non-calculator portion. For number 3, hot water is dripping through a coffee maker, filling a large cup with water. With coffee. The amount of coffee in the cup at time t between 0 and 6 is given by a differentiable function c, where t is measured in minutes. Selected values of c of t measured in ounces are given in the table above. So this is not a rate here. This is going to be the amount of coffee that is in the pot at a given time, either 1, 3, 4, 5, or 6 minutes. So for part A, it says use data in the table to approximate C prime of 3.5. Show the computation that leads to your answer. So C prime of 3.5 would indicate the rate of change at which the water is dripping through the coffee maker. And so 3.5, we know that that's going to be a rate of change for ordered pairs that's sitting here with 3 and 4. So we can simply do that. So the rate of change in the hot water the rate of change in the amount of coffee in the cup divided by the change in time. So 12.8 minus 11.2 divided by 1 means that the rate of change is simply 1.6 ounces per minute. Part B, is there a time where t is between 2 and 4 where c prime of 2 is equal to 2? So it's asking, is there going to be a time when the rate of change in ounces per minute is going to be exactly 2 ounces per minute? And this refers to can we apply mean value theorem here? Okay, meaning that, so mean value theorem says that if we can find the average slope or the average rate of change at t equals 2, between t equals 2 and t equals 4, and if that's equal to 2, then we know that there's going to be an exact moment in time between 2 and 4 where my rate of change is also going to be the exact value as the exact same value as the average slope. So mean value theorem, all we do is we find the average slope between our endpoints. So c of 4 minus c of 2 over 4 minus 2 is 12.8 minus 8.8 divided by 2, and that's equal to 2. So the average rate of change is 2, so we know that somewhere between, because we have a differentiable function that's a smooth curve basically, then we know somewhere between there also must be a rate of change that is equal to the average. So by MVT, since average slope between 2 and 4 is 2, then there's at least one t value where c prime of t is equal to 2. So I should have said 1 here, at least one t value. For part C, use a midpoint sum with 3 subintervals of equal length indicated by the data in the table to approximate the value of 1/6 definite integral of c of t. And also use correct units to explain the meaning in the context of the problem. So first off, midpoint sum, we have to think of this as adding the area of 3 rectangles. So let's split this up into 3 subintervals, so between 0 and 2, between 2 and 4, between 4 and 6. Each subinterval has a width of 2, so 2 times. Now we have 3 heights to choose from. We want to choose the middle height for each interval because they say midpoint sum approximation. So 2 times 5.3. Second interval has a width of 2. 4 minus 2 is 2. And the middle one is, the middle value is 11.2. And then the third rectangle has a width of 2 and a height of 13.8. So once we have that, we can multiply that and add those together. But notice that there's a 1/6 here. So this is indicating that this is an average value. So we total up the total amount of coffee of liquid that accumulates, divided by 6, so we get 10.1 ounces. So what that means is that this is the average amount of coffee in the cup between the interval of 0 and 6 minutes. Okay, part D. The amount of coffee in the cup is multiplied by B of T. So now we have a formula that gives us the exact amount of coffee at a given time. Using this model, find the rate at which the amount of coffee in the cup is changing when T is equal to 5. Okay, so we want to find the rate at which the cup is changing, or the amount of coffee is changing, so we need to find the derivative. Again, this is without a calculator, so we'll do this by hand. So 16 goes to 0, okay, and then 16e to negative 0.4 t. So the derivative rule for e to the u is e to the u times u prime. So we have negative 16 e to the u times e to the u times u prime. So the derivative of negative 0.4 t is simply negative 0.4. Now we can replace the t value with 5, and 0.4 times 5 gives us negative 2/5, and we can also replace, we can think of this as negative 2/5 as well. So I believe you can just leave your solution as this. You don't have to simplify all the way, but I simplified it all the way to be 32 over 5e squared. And then don't forget the units here, which is ounces per minute. Okay, number 4 from 2013. Okay, the figure shows the graph of f prime. So we're looking at f prime, not f of x, which is the derivative of the twice differentiable function on the closed interval from 0 to 8. The graph of f prime has horizontal tangent at x equals 1, x equals 3, and x equals 5. The area is labeled in the figure. The function is defined for all real numbers and satisfies f of 8 is equal to 4. So we have an ordered pair that kind of gives us an anchor to help us find other positions throughout this problem. So for part A, find the values of x for which the function has a local minimum. So if we're looking at the derivative graph, then we know that anything above the axis represents positive slope, anything below represents negative slope. Okay, so we see that we get negative slope in this region here, and anywhere the graph crosses the x-axis would be where the slope is equal to 0. So I like to make a sign line to represent that, so I can kind of get a visual as to what the original graph may look like. So 1, 4, and 6 are the critical points where slope is 0. 0 and 8 are the endpoints. And then the only time where the graph dips below the x-axis is between 4 and 6, so that's the only part where the original graph will be decreasing. And then we see a relative minimum must be where the slope changes from a negative to positive. So therefore, relative minimum is at x equals 6 because f prime changes from negative to positive. Okay, part B. Determine the absolute value of f on the closed interval from 0 to 8. And if we want to find the absolute minimum value and it's a closed interval, this is referring to having to go through extreme value theorem. So extreme value theorem says if we want to find the absolute minimum, we're going to have to test the relative minimum and test the endpoints. Okay? There's no need to test the relative maximum because there's no way the relative maximum will ever be the absolute minimum. So we don't have to worry about relative maximum, just relative minimums. So we found from part A that relative minimum is at 6. So we basically just have to plug 6, 0, and 8 into the original function to test the endpoints. Okay. So if I want to test the endpoints, I want to find f of 6, relative minimum first. So f of 6, if I want to find the position at 6, I need to have my starting point. And they tell us in the problem that my starting point is f of 8. So if I want to get from f of 8 to f of 6, I have to say plus the definite integral from 8 to 6. So I'm going backwards from 8 to 6 of f prime. However, it makes, though even though this is the way that we want to set up because we're starting at 8 and we're going backwards, we like to evaluate definite integrals with the lower and upper bounds in its right place. So we want to, it makes it easier if we can rearrange this so that our lower bound is the smaller value. So I'm going to rearrange it. So if I rearrange the 6 to the bottom and 8 to the top, that means I have to change the sign. So plus becomes a minus, and the area or the definite integral of between 6 and 8 of f prime will be a positive 7. Okay, and you can see that here, positive 7. But we're subtracting it, so therefore 4, which is our initial position, minus 7 is negative 3. So we're going to keep track of this, and we'll come back to it and we'll compare it to see whether this is the absolute minimum value. Okay. We will also want to test the endpoints. So f of 0, my endpoint f of 0 must be f of 8 plus the definite integral from 8 to 0. So if I want to get from 8, I've got to go backwards from 8 to 0. But again, my lower bound is the higher value, so I'm going to switch this around and put a negative outside. And then the definite integral from 0 to 8, we can look at this graph here. So we have 2 plus 6 minus 3. So 8 minus 3 is simply 5. And once we have that, from 0 to 8. So from 0 to 8, we have 2 plus 6 minus 3 plus 7. Okay, and then once we add those together, we're going to get a positive 12. But then there's a minus in front, so 4 minus 12 is negative 8. And finally, our other endpoint is f of 8, which they give us, which is 4. So we're going to compare 4, negative 8, and negative 3. And we see that the absolute minimum must be at 0 because negative 8 is the smallest value between these 3 points that we tested. Part C, on what open interval contained between 0 and 8 is the graph of f both concave up and increasing. So we're going to make a sine line. Remember, if we make a sine line for concavity, if we're looking at the derivative graph, then anywhere where there's a relative max or relative min, meaning that anywhere there's hills and valleys, those are going to be our point of inflection. And we simply look at the slope of our f prime graph to determine whether it's concave up or concave down. So the graph is falling between 0 and 1, so concave down, rising, concave up, falling, concave down, and rising, concave up. So we're just simply looking at the slopes of the f prime graph, and that tells us whether the graph is concave up or concave down in that interval. Okay. So we're looking to see where the graph is concave down and increasing. So we want to compare between our two sine lines here. So we see that between 0 and 1, the graph is concave down and increasing. And also between 3 and 4. So between 3 and 4, you see the graph is increasing, but then also between 3 and 4, you see the graph is concave down. So we kind of have to put these sine lines next to each other and see which intervals will fulfill both conditions that the problem is asking for. Okay, so between 0 and 1 and between 3 and 4. Okay, part D. The function g is defined by g of x is equal to f of x quantity cubed. If f of 3 is equal to negative 5 halves, find the slope of the line tangent to the graph at x equals 3. So we know the ordered pair, okay? And if we want to find the slope, we can simply plug, or we can find g prime of x and plug in and find g prime of 3. So first I need to find g prime of x. So to find g prime of x, we have to go through chain rule because we have f of x quantity cubed. So the derivative of f of x cubed is 3 f of x squared times f prime of x. Next step, we want to evaluate each of these values. So replace 3 for each of the x values. F of 3 is simply going to be negative 5 halves. That's given to us in part D. And f prime of 3 is going to be 4 because we can look at the graph to determine where f prime of 3 is. So f prime of 3 is equal to 4. Remember, we're looking at the derivative graph, so f prime of 3 is the ordered pair 4. So once we have that, we can just plug all that in. multiply this together, we get 25 over 4. 3 times 25 is 75, and the 4's will cancel out, so we're going to get g prime of 3 is equal to 75.